Hi, Chris Good here, and we've got one more one-way ANOVA practice problem to solve, and this is about neuroscience researchers who examine the impact of environment on rat development. Rats are randomly assigned to be raised in one of the four conditions: impoverished, standard, where you get to play with other rats, enriched with rats and toys, and super enriched, caged, rats, toys. We change on a periodic basis. After 2 months, the rats are tested on a variety of learning measures and several neurological measures. And the data appear below. Well, let's see. I think that these numbers are actually the number of trials to learn a maze to a 3 perfect trial criteria, so that a smaller number is going to be better. And I think that just because the way the data worked out. And it says the data for the maze task. Great. Okay. Well, the appropriate test then is the analysis of variance. So let's get to it. Let's do all 4 of our steps. So step 1 is to state that null hypothesis, that the mu from the impoverished one is equal to the mu, the population mean maze time for the second condition, which is equal to the mu for the third condition, which is equal to the mu for the fourth condition. Did we just have 4? Yes, we did. Okay, so I'm done with the null hypothesis. Alpha is going to be 0.05, just like it usually is, and our F crit we need to evaluate on however many degrees of freedom that we have. So let's figure that out first. In order to do that, we need to count the number of groups, which is 4. We need the number of scores, which can be counted thusly. Count the number of scores. 5 in each of 4 groups is 20. And now we can say the degrees of freedom between treatments is 4 minus 1 or 3. And degrees of freedom within treatments is 20 minus 4 or 16, n minus k, big N minus k. So let's go to our F table, right? And we'll see what our critical value is. How do we look this up? Well, we've got 3 degrees of freedom in the numerator between treatments and 16 degrees of freedom in the denominator within treatments. So it's 3.24, 3 degrees of freedom in the numerator. Scroll down to 16 in the denominator, 3.24. So F crit at 3 and 16 equals 3.24. Okay, so what's next? Let's do sum of squares between treatments like we've been doing. Let's go ahead and compute our averages because we're going to need those, the means for each group, right? Averaging only the scores and no other numbers. The t is just the sum of the scores in one treatment condition. We can copy and paste that over here because we have the same number of scores in each condition, which we can count, or just know that it's 5 in every condition. And now we do t squared, that's just t squared. Copy that. And t squared over n is equal to t squared over n. Copy that for 4 conditions. G is just the sum of all of these. G squared is G squared. And we'll do sum of squares later. Let's complete sum of squares between treatments. It's equal to the sum of these 4 t squares over n's, and then we subtract this quantity in parentheses, g squared over big N. And we could compute our mean square. I'm going to save that till later. Right now, let's do within treatment sums of squares. So for each one of these conditions, I'm actually going to calculate the deviation. Right, standard deviation. Oh, that's funny. This is a little statistic stroke, the standard deviation. The enriched deviation. And the super enriched deviation. We're also going to square these. So we're going to have an impoverished deviation squared. We're going to have a standard deviation squared, which is variance. Oh, enriched deviation squared and a super enriched deviation squared. All right, now let's get these deviations first. So impoverished deviation is, you know what? Let's do this. Put it in the right cell. For the first one, it's this score minus the mean for that group. And we're going to hold that mean constant as we paste on down the column for the other 4 scores. Same deal with the standard group. To get those deviations, we'll subtract the mean, and you want it to be the same mean for each one of these scores. And for the enriched group, enriched score minus enriched mean, make it the same mean for each group. Copy on down. And for the super enriched, enriched score minus super enriched mean, hold that mean constant, paste it on down. And let's just go back and check and make sure. Did we do that right? Yeah, looks like we did. Okay, those are deviations. Now all we have to do is square them. Square this one in the upper left-hand corner for the impoverished, and then we can copy that and make sure that we paste it in all 4 of our groups, so that now our within treatment sum of squares is the sum of all these squared deviations. It really is. We could do sum of squares for each one of these groups. That would tell us about something about the variability of each group. Let's just do that, right? Sum of the deviations for this group. And then when we copy and paste it, it gives deviations for each one of these groups. We can check to see that those sums equal this sum, and we'd be right. Okay, let's do mean square. It's sum of squares between treatments divided by degrees of freedom between treatments. This one is sum of squares within treatments divided by degrees of freedom within treatments. Now we can compute f as mean square between treatments divided by mean square within treatments, and get this to a reasonable number of decimals. 12.72 is bigger than 3.24, so that was compute f. And our decision then is to reject that null hypothesis, and our sentence is going to read something like, rats possessive plural, so S apostrophe, environment had a significant effect on maze completion time with f of 3 and 16, degrees of freedom equal to 12.72, the observed value, and p less than 0.05 because we rejected. Now we've got to do our Tukey's HSD post hoc test, which means we need to look up Q. We had to do this in one earlier. Q is the studentized range statistic, and you look it up kind of like an F, but remember that the numbers in the columns are the number of treatments, not degrees of freedom. So we had 4 different treatments, and we had 16 degrees of freedom, so 4.05 is our value for Q. 4.05. And HSD then is equal to Q times the square root of this quantity, mean square within treatments divided by our sample size, which is our sample size from each group, which is n. I don't care which n you use, just pick one of them. It's 5 in each group. So our honestly significant difference is 5.27. That means that in order to be significant, these two means, any pair of two means, any two means have to be 5.27 apart from each other. And we've got a lot of differences to compare. Impoverished versus standard, impoverished versus enriched, impoverished versus super enriched, standard versus enriched, standard versus super, and enriched versus super. Let's write all those down. So we've got impoverished versus enriched. We've got impoverished, oh, wait a minute, let's do standard first. Impoverished versus standard, impoverished versus enriched, impoverished versus super enriched. We've got standard versus enriched, and standard versus super enriched, and enriched versus super enriched. And I think that's all that we've got. 6 different differences. So impoverished versus standard is equal to this, impoverished versus standard. All right. That's 2.8. That's smaller than 5.27, so not significant. Impoverished versus enriched. The impoverished mean versus the enriched mean. That's 7.4, so that one is significant. Impoverished versus super enriched. 10.4, so that's significant too. Standard versus enriched. Let's see. Standard versus enriched. Nope, not significant, because 4.6 is smaller than 5.27. Standard versus super enriched. 7.6, that's bigger than 5.27, so that one is significant. And the last one, enriched versus super enriched. Enriched versus super enriched. Not significant. So we got 3 significant differences to report, and 2 of them involve the same category, super enriched. So I'm going to say something like this for our sentence. Rats in a super enriched environment completed the maze significantly faster than those in either the impoverished and impoverished, let's say, or a standard environment. So that's these 2. Super enriched is faster than standard, and super enriched is faster than impoverished, because I subtracted standard minus super enriched here and got a positive number, which means super enriched is smaller, which means they ran the maze faster because their time was lower. Same deal here. But I need to add this one in here. So I'm going to say, and rats in an enriched environment ran the maze faster, significantly faster than those in an impoverished environment. We found this using the same Tukey's HSD of 5.27 at an alpha 0.05, so P must be less than 0.05, and you're done with the sentence. One long sentence, one short sentence. I'll see you in the next solution.